Okay, so now we understand what it means when we say a wave function is normalized. A wave function is normalized. Let's say a wave function psi sub n is normalized when the integral, if I integrate that wave function times itself, remembering to take the complex conjugate if I need to of one of them, that integral comes out to be exactly 1. And that's, remember, because this particular product is the probability of finding the wave function at a particular place. Probability of finding it anywhere has to be 100%. So a normalized wave function is 1, where this integral is equal to 1. That's when I multiply a wave function by itself. We can also ask the question, what happens when I take a wave function and I multiply it by a different one? So maybe I have wave function psi sub 1 or 2 for n equals 1 or 2, and a different wave function, let's say psi with m equals 5. So product of two different wave functions, again, including a complex conjugation, and integrate that product. And I can ask, what do I get when I take the product of two different wave functions times each other? So this thing that we're calculating, let's give that a name. So this integrated product between wave function m and wave function n, I'll call that O, capital O, sub mn. And we can see what that's equal to for a specific example. The only problem we know how to write down wave functions for so far is the one-dimensional particle in a box. If I say the wave functions for that 1D particle in a box have this form. They look like sine waves, sine of some integer n, pi x divided by the box length with a normalization constant out front. Let's say I want to know the value of this O just for the simplest two wave functions, the first two, one of them for n equals 1, one for n equals 2. So with our definition, that's the integral of the product root 2 over a sine pi x over a when n equals 1. And then root 2 over a sine 2 pi x over a when n equals 2. And I don't have to worry about the complex conjugate because there's no complex or imaginary numbers in this wave function. I integrate this. This is the particle in a box, so I integrate from 0 to a because the particles live in a box. The range is only between 0 and a, and the wave function is 0 outside that box. It's only non-zero inside the box. So psi sub 1 looks like this. Psi sub 2 looks like this. So we have this integral to evaluate. We could evaluate it formally. The way we'd go about it is probably use the double angle formula to do something with this sine of 2 pi x over a and turn it into some trig functions of pi x over a. And that would work fine. We could work a little while and get the answer. Or we could use symmetry. We could use a shortcut and say, since we know what these wave functions look like, especially if I had drawn them as symmetrically as they're supposed to be, the area on the left-hand side of the box, where both psi 1 and psi 2 are positive, is symmetrically equivalent to the area on the right-hand side of the box, where psi 1 is positive but psi 2 is negative. So every point, like this point here, where psi 1 is positive and psi 2 is negative, is mirrored by a point over there here, where the two values are the same, but psi 2 has the opposite sign. So the area under the product on the left side of the box is positive and exactly equal, but opposite sign to the area on the right side of the box. So whether we do it with actual trig and integration, or whether we say we observe the symmetry of the problem and use that to just observe that this integral has to come out equal to 0, this overlap integral, this O sub 1, 2, is going to have the value of 0. So not 1, like for the normalized wave function multiplied by itself. When I take these two particular different wave functions, multiply them together and integrate, what I get is 0. So that's a different property, two wave functions, we say that they're orthogonal to one another. That should be an O, orthogonal, when that product of the two wave functions, one of them complex conjugated, integrated, when that gives us 0. So that's the definition of this property, orthogonal. And so what we've just seen is that the psi sub 1 and the psi sub 2 wave functions for the one-dimensional particle in a box, we can say those two wave functions are orthogonal to one another. And orthogonal means the same thing here as it does in the sense that you may have heard that word before when you're talking about vectors. I would say two vectors in 3D space are orthogonal to one another as a way of saying they're perpendicular to one another. The way you know if two vectors are orthogonal to one another is you multiply them in a particular way. You take their dot product, and if their dot product is 0, then you can say the wave function, the vectors are orthogonal. So just like a dot product is a particular way of multiplying vectors together to see whether they're orthogonal, this integrating, complex conjugating, and then taking the integral, that's a particular way of multiplying two wave functions together to find out whether they're orthogonal or not. And again, a wave function can be normalized. You just have to multiply it by itself and integrate. It can be orthogonal to another vector if that product, complex conjugated, integrated, works out to be 0. So we could continue with more examples for wave functions of the particle in a box, one-dimensional particle in a box. But it turns out that whichever pair we choose, whether it's 1 and 2, or if I chose 1 and 3, or 1 and 4, or 2 and 3, or 2 and 4, and so on, any pair of different vectors, wave functions that I choose are always going to turn out to be orthogonal to one another. So we can say a set of vectors, so let's say all of the vectors I can go a little further and say the one-dimensional particle in a box wave functions, psi sub 1, psi sub 2, psi sub 3, and so on, that complete set of vectors, those are all mutually orthogonal to one another. What I mean is that any pair of different wave functions I choose out of that set are going to be orthogonal to one another. It's not just 1 and 2, it's every pair within that set. Each one is orthogonal to all the others, so we say they're mutually orthogonal. There's one other important feature of these wave functions that we can point out. Since they're both normalized, every one of these particle in a box wave functions is normalized once we've chosen this particular coefficient down in front, and the set is mutually orthogonal, we can say that a set of vectors is orthonormal, another vocabulary word, if this quantity O sub mn, if I do that for two wave functions that are the same as one another, n and n, if these two subscripts are the same, then if they're normalized, when m is equal to n, when those indices are the same, then the integrated product is equal to 1. But when they're not the same, when m is not equal to n, for every pair, if it comes out to be 0 because they're mutually orthogonal, then we say that that set of vectors is orthonormal. In other words, an orthonormal set of vectors is one where every vector is normalized, and also the full set is mutually orthogonal. And it turns out that having orthonormal vectors is particularly nice for reasons that we'll see soon coming up. It's also convenient that not just for the one-dimensional particle in a box, but for any quantum mechanical problem, whichever quantum mechanical problem we choose to solve, we'll get a set of wave functions, and the wave functions will be, we can normalize them, and we can also make sure to make them orthogonal to one another. If they don't come out automatically orthogonalized like the one-dimensional particle in a box wave functions are, then there's a procedure we can take to make sure that they're mutually orthogonal to one another. So it's very convenient that quantum mechanical problems can always be chosen so that the wave functions turn out to be orthonormal. The solutions, the wave functions all are orthonormal. And that's convenient because then we can use those orthonormal wave functions to construct other functions. And that's what we'll talk about next. All right, I'm back with a quick addendum to point out one more piece of terminology that I forgot, and that's to give a name to this quantity OMN that we've been talking about. This OMN that's equal to either a 1 or a 0 if the wave functions are orthonormal. That quantity is called an overlap integral. The reason we call it an overlap integral, first of all, it's an integral. Two wave functions multiplied together and integrated, so it's an integral. And what we're doing when we calculate that overlap integral, when we calculate the product of one wave function times another wave function, that overlap integral, the inside of that overlap integral is non-zero only in places where both of the wave functions have some non-zero value. So in this case, for the particle in a box, both these wave functions were non-zero everywhere except for when the psi2 function passed through a node in the middle of the box. But let's say we had a different problem where, let's say, psi1 had some particular shape and it was 0 for part of the range of whatever variable we're interested in, and our psi2 variable, a psi2 wave function, has its own different shape and is 0 somewhere else. So the way I've chosen to draw these wave functions, psi1 is non-zero only in this region, psi2 is non-zero only in this region, and there's, when I multiply psi1 times psi2, when I do an overlap integral, then psi1 may be non-zero, but it's being multiplied by a 0 psi2, and vice versa. Wherever psi2 is non-zero, it's being multiplied by psi1 equal to 0. So for this particular case, the overlap integral would turn out to be 0. So that's an important observation about these overlap integrals. They can be 0 either because there's no region where the two wave functions overlap one another, or in this case, even though the wave functions have a high degree of overlap, they can be 0 for symmetry reasons where the positive contributions from one happen to cancel the negative contributions from another region of the box.